Good morning, class. Today we're going to be starting our first lecture on waves and vibrations. Waves and vibrations. Okay. Now it's important for you guys to know that going forward, we're going to make sure that we take each chapter step by step, that we don't skip anything, because it's very easy to fall behind when you're doing physics if you don't understand something that you did today or that you do tomorrow, and you try moving on to topics that we're going to do a week from now. It's going to be very, very hard to catch up. But with that said, let's start off with our first equation that we're going to see. Our first equation is based on something that we call Hooke's law. So Hooke's law makes this equation right here possible. Now what this equation is the force of a spring is going to be equal to negative K times X. Now what is K? K is something that we call the spring constant. Okay, and if you've never seen this term before, or just as a refresher, what a spring constant is, it is simply a value that varies depending on the spring that you're using, but it's a measure of the stiffness of your spring. So for example, if you have a spring that's made out of iron, it's gonna be very stiff, so it's gonna have a very high K value. But if you have a spring made out of plastic, let's say, it's not gonna be stiff at all, so it's gonna have very low K value. Okay. Now, the X value is gonna be the distance that the spring is displaced from equilibrium. So what does that mean? Let's say we have, this is the ceiling, right? And we have a spring hanging, and it's attached to a box, right? If no force is being applied to this box right here, and the spring is just, still, it's not moving up or down, this is the position that we call equilibrium. Okay? Now let's say I take this same model, but then instead I extend it a little further. Now this distance that it was stretched compared to the first case right here, this distance is our X value that our spring was stretched from equilibrium. Okay, so I know usually when you did kinematics, X meant more like the distance that a car traveled or something like that, but when we're dealing with springs, it refers to distance that a spring is stretched from equilibrium. So the same way this spring is being stretched outwardly, it can also be compressed from equilibrium to make it smaller, and still the same thing, right? It's being stretched negative X, it's being compressed or expanded, right? So now if you're thinking critically, you might wonder why this equation has a negative value. Okay, and now this is an important feature of this equation, and there's other equations in physics that have this feature. This equation is something that we call a restorative force. Okay? So what is a restorative force? It simply means that this force is always working against the direction that you are moving. It kind of wants to bring things back to the way they were, right? So let's say I'll make a new model. Let's say we have a spring that's horizontal, right? A horizontal spring. Right? Your value for K, just an important thing, is always positive. Okay? K is always a positive number. It can never be negative because, the stiffness of a spring can't be negative. I think the logic is pretty sound there. So now that we know that our K is always positive, let's take a look at our X. So let's say we say that going to the right is positive and going to the left is negative, right? Now, I said that Hooke's law is a restorative force, and a restorative force always goes against the direction the object is moving. Okay, so this means that if the spring is being stretched to the right, our restorative force is going to want to bring it to the left. If we're compressing our spring to the left, our restorative force is going to want to expand it to the right to bring it back to that equilibrium point, right? And if we just check the math real quick, right? Okay, let's say we take our box and we bring it more to the right, right? This means that in this scenario, our x is positive, right? So let's say we plug in a positive x for this equation, right? We're going to have f of s is equal to negative k, and then this is a positive x, right? So then we have a negative and a positive being multiplied, and we have negative kx, right? So this means that our restorative force is negative, and negative is to the left. So this force wants to bring the box back to the left, right? So now let's check the second scenario. The second scenario is when we compress our spring, right? So now our spring is compressed, and now our x is negative. Right? So if our x is negative, we're going to say the same equation is going to be equal to negative k times a negative x. So then we're going to have a negative and a negative that makes a positive. So f of s, or fs, is going to be equal to kx. Okay? And now, obviously, as you can see, this is a positive number. So this means that our restorative force is positive, so it wants to bring this spring back to the right where it is not compressed. Okay? So yeah, just remember, our restorative force, and this is important, our restorative force always pushes or pulls the object back towards that equilibrium position. Okay? Now, we are going to start moving on to something that we call simple harmonic motion. Okay? Now, simple harmonic motion is something that occurs when the forces along a certain direction, so for example, the forces horizontally obey Hooke's law. Okay, so basically, let's say you have a slinky, right? Simple harmonic motion would be like, okay, your slinky is stretched out at T1, and then at a second time it's at equilibrium. Oh, sorry. At a second time it's at equilibrium, and then at T3 it's compressed, and then at T4 it's back to equilibrium, T5 it's back to stretched. You get me? So it follows that wave motion, and this could like keep going. Okay. And an example would be, like if you have a spring hanging from the ceiling, right, with like a box attached to it, it would be like in the real world, it would look like, okay, it's here, and then it's stretched, and then it's back, and then it's compressed, and then it's back. Just, you guys can imagine it, just a spring that keeps expanding and collapsing, expanding, collapsing. Okay? And now, with that being said, there are three very, very, very important terms that we need to learn that apply to simple harmonic motion. Okay? I'll start on a new page. The first term, amplitude. Okay? The second, period. And the third, frequency. Okay? So we'll start off with amplitude. What is amplitude? Amplitude is simply the maximum distance that the spring is gonna compress or stretch. So, for example, let's say, again, we can just look up here, like in this scenario right here on the left, we see that this is the maximum amplitude. This is the furthest our spring reaches. And this right here would be our negative amplitude. This is the smallest our spring gets. Okay? Now, this is important because that means that this spring cannot stretch past that amplitude point. Because if it stretches past this, right? If there's some T0 here that goes further, then that means that this wasn't our real amplitude. This is our amplitude. Okay? So whenever an amplitude is defined, just know that, let's say you're working on a problem and somehow you end up with a value greater than the amplitude, then chances are you need to go back and check your math, because that breaks the definition of what an amplitude is. Okay? So again, I'll just write it down. So amplitude is the maximum distance that a spring can stretch or compress to from its equilibrium. Okay? Now, second term, period. Alright, so, or actually, before we move on to period, there is a variable for amplitude, and it's very simple. So, as I mentioned before, our variable for distance is x. But when we're saying that, let's say, if I ask you what is the value of x when x is at the amplitude, it's very simple. When x is at the maximum amplitude, it's going to be a, or x is gonna be negative a when the spring is compressed. Okay. Now moving on to period. Period has a variable t, capital T, and period is the time that it takes for one cycle to occur. So what does this mean? If we look at this, one cycle occurs when you go back to where you started. Okay, so for example, in this case, we start here, we go to equilibrium, we compress back to equilibrium, and back to where we started. Okay, so this is one cycle, so this would be one period. Okay, so for example, if I ask you what is the period of the seconds hand in the clock, okay, if we say the second hand starts when it's pointing at the 12, then we say, okay, it takes 60 seconds for it to do one whole cycle, for it to go around the whole thing and back to where it started. Does that make sense? Now, frequency. Frequency has a variable f, and it is how many cycles you do per second. Okay, so for example, frequency would be like if we stick to the example of the second hand, right? So out of the if we take the clock, right, and obviously I can't do it perfectly, but let's say I divide it into 60 parts. Pretend that's 60, right? And it starts at the 12 up here. We agreed that the period is equal to 60 seconds. Okay? And why is that? It's because one cycle is when it goes around the entire time and back to where it started, right? Now, frequency is how many cycles you do per second. So, if we're paying attention to the seconds hand, we would say, oh, how many cycles does the second hand does in a second? Well, in 1 second, it just moves, to the next second mark. And how much of the cycle is that? We said that the cycle is 60 seconds. So the frequency is 1 out of 60 seconds. Does that make sense? Because in 1 second, it only goes 1 second. It can only go 1 second at a time. And if it wants to complete the whole cycle, it has to, do that 60 times. And now, you may notice that this period is similar to this frequency in that they both have 60 seconds in the equation. And there's a reason for that. The reason for that is that frequency is equal to the reciprocal of period. Okay? So for example, if I say, what's the period? What is the period and the frequency of the minute hand? Right? It would say, okay, the period, how long does it take for the minute hand to go to, when it starts at 12, how long does it take to go around? It takes 60 minutes. That's 1 hour. So it takes 60 minutes Okay, and now is a good time to practice our unit conversion. Maybe I want the answer in seconds. Okay, so instead of minutes, let's convert to seconds. And to convert, this is the way that I think is the easiest to convert your units. All you have to do is you multiply by what we call your conversion factor. So I want to go from minutes to seconds, right? So in order to do that, I need to cancel out these minutes and replace it with seconds. And the way I'm gonna do that is I'm gonna put a fraction over here. And I'm gonna put minutes here and seconds here. Okay? And all that's gonna happen is your minutes is gonna cancel out with this and this. And now here you just have to write how many seconds are in 1 minute. So for example, we have 60 seconds in 1 minute. And then we can convert. Okay, so now we know we have 3,600 seconds. That's how long it takes for the hour hand to complete one cycle. Okay, so now it's also asking what is the frequency. So simple, we have our period, right? Our period is 3,600 seconds. And now our frequency is going to be 1 over t. So it's going to be 1 over 3,600 seconds. Okay. And with that, we're gonna stop today. We're gonna start the discussion portion of the class. Now's the perfect time to ask any questions. I know this can be a bit much, but don't worry. That's what I'm here for.